Hello everyone, in today's video I'm talking about turbo derivatives, a real-time cross-asset pricing and risk library which was first developed in 2012. If you work at a hedge fund or a bank, keep watching. The library has been licensed to several financial institutions in both binary and source code form. The software runs in real time and never leaves the end user waiting for results. It runs on multiple CPU cores, can be used from Excel, Python and C++, and contains 450 plus cross-asset functions, including functions to fit curves and generate risk for portfolios of cash and derivative trades. This video takes a deep dive into the yield curve functionality the library provides, a core building block in any derivative system. The software provides functionality to support building of swap curves, bond curves, metal lease rate curves, crypto curves, and yield curves needed for CDS valuation. We'll start with a spreadsheet demonstration and then show how spreadsheet functionality for building and publishing yield curves can be exported to what are called Excel work engines, which can be invoked from Python and C++ code running on servers making no use of Excel. Here is a demonstration spreadsheet utilizing the library. All of the 450 plus library functions begin with TD and are grouped. For example, all curve-related functions begin with TD curve and all FX-related functions begin with TDFX. Using USD as an example, we can see each of the curves and their instruments are laid out side by side. To support the full range of curves for the world's currencies, multiple instrument types can be used to fit curves, including cash, futures, FRAs, swaps and FX forwards. Year-end turns, flat forwards and collateral-aware discounting features are also supported by the curve building process. The example sheet builds 4 example curve sets for the US, Mexico, Norway and South Korea. The Mexico curve set uses MXN swaps with MXN cash flows and USD used as the collateral currency. The Norwegian curve set uses mark-to-market cross-currency swaps with principal exchanges and notionals adjusted for spot FX. The South Korea curve set uses non-deliverable swaps with principal exchanges and USD as the delivery currency. The type of interpolation used for each curve can also be adjusted. Curves built from instruments with fixed maturities like FRAs can be configured to roll automatically without any manual adjustments to the curve being needed to remove expired instruments. We can effectively configure maintenance-free curves which will build daily for the next several years without needing to be manually adjusted in any way. Curve details are fed into a function which builds all curves in the curve set simultaneously. Once the curve set is built, all the curves in the curve set can be displayed using the display curve set function. To view all the discount factors in any given fitted curve, the function tdcurvedf can be used. If you want the discount factor for a specific date from the curve, then you can pass the function a specific date and the interpolated discount factor is returned. The function tdcurveForwardRate can be used to return risk-free and term rates on a given forward date, and we use this function here to plot a graph of forward rates. When it comes to pricing and risk of banks and hedge funds, you don't want to have every trader or PM building their own version of a curve. Instead, a single version of a curve set is needed, which can be seen and used by everyone for consistent pricing. To help address this, the software provides a messaging library which allows key objects like curves and vol surfaces to be shared and broadcast to multiple users or subscribers around the world. The messaging library can be invoked through functions named TDNW. TDNW publish, for example, is used here to publish each curve set to a topic on the message bus. Machines at different locations around the world can then access the published curve by using the software to subscribe to the same topic. Every time we calculate the spreadsheet, we publish an updated curve set from this machine to machines at other locations around the world. So we have just shown how to build and share curve sets using a spreadsheet, but a robust curve service needs to continuously refit and republish curves every few seconds. Excel is great for prototyping and checking curves build correctly, but Excel spreadsheets aren't suited to continuously recycling and republishing curves 24 hours a day. Typically at this point in the development cycle, the IT groups invest substantial time and effort in productionizing spreadsheets and writing C++ and Python code to replace the spreadsheet. Turbo Derivatives provides an alternate mechanism for productionizing spreadsheet functionality by using what we refer to as Excel work engines. Work engines allow functionality in Excel spreadsheets to be exported to a work engine, which can then be run as part of a C++ or Python program without making any use of Excel. Work engines provide all the benefits Excel has to offer, coupled with the robustness and scalability benefits that come from using C++ and Python code. We can take spreadsheets and in seconds convert them into engines which run without the need for Excel. Excel's calculation engine and the function it provides have effectively been rewritten in a form which allows Excel expressions to be evaluated from a robust Python or C++ process. Let's look at a real-world example of Excel work engines and show how work engines can be used to build a robust and scalable curve set publisher with little to no effort. If we click the Export Work Engine button on each curve sheet, the software exports instructions describing the operation of each worksheet to work engine files. Before running a work engine without Excel, we can quickly test the work engine in Excel using a few simple function calls. We load the work engine, evaluate the engine, and then display the results. Work engines can be invoked from C++ and Python code, but the software also provides a pre-built program for repeatedly invoking one or more work engines at predefined intervals. We will use it to replicate the behavior of the spreadsheet and build and publish curve sets every few seconds. We will run the work engines on a server in London and subscribe to the curve sets it produces from a machine in New York. The program reads the work engine files and executes the spreadsheet functionality in each engine without using Excel. The entire process of fitting and publishing the curves has been moved out of Excel to a process running on the London server. Excel isn't even installed on the server running the Excel work engines. The command window shows the curve sets being built and published to subscribers around the world every 10 seconds. If we start Excel on a client machine in New York, we can subscribe to the curve sets being published from the server in London. The sheet in New York listens to updates to the curve set. Every time the curve is updated on the server in London, the curve set on the New York machine updates. The fitted curve sits in memory behind the sheet, and we can use the toolkit functions to read details of the curve and use the curves for local pricing and risk. Let's look at how easy it is to change work engines running on the server. We return to the original Excel template and turn on a flag to build and publish bumped curve sets with shifts applied to the SOFR curve. We re-export the Excel work engine and just restart the process running on the London server to pick up the changes. In New York, the spreadsheet subscribing to the USD curve can now subscribe to the additional bumped curve sets being produced on the server in London. At the heart of a work engine is a parser capable of parsing Excel spreadsheet formulae. An obvious question is, if Excel expressions can be evaluated from a work engine without using Excel, what Excel expressions are supported by work engines? How good are work engines at evaluating Excel expressions when compared to Excel and Google Sheets? To answer these questions and demonstrate the turboderivative library being called from a website, we installed the library on a well-known web hosting provider. The web page shown is running on a machine in New York calling the turboderivatives library installed on a low-spec 32-bit shared web server in Arizona. The website allows you to enter the formula you wish to be evaluated at the top of the page. When you press the Evaluate or Parse buttons, the formula is sent to the server in Arizona and the turboderivatives library evaluates the expression and returns the result. 3 sections of simple, intermediate and complex expressions are provided which demonstrate the type of expressions work engines can evaluate. A complete list of the native Excel functions supported by work engines is shown in the section at the base of the page. The majority of Excel's built-in functions are supported by work engines. Work engines also support the 450 plus additional functions provided by the turboderivatives add-in. To check any expression, we can copy and paste it into Excel to check the results. As a comparison, it can be seen Google Sheets is unable to handle some of the more complex expressions which both Excel and turboderivatives work engines are able to evaluate. Although a lot of the examples shown here are Excel-based, Excel is very much a window onto the library. The spreadsheet add-in shown in previous examples is a thin layer which simply gathers worksheet details before calling into the library. The same library functions called from Excel can also be called from programming languages like Python and C++. The environment which holds and stores all the data like curves and vol surfaces behind Excel also works behind Python and C++, and the Excel interface can also be used from Python and C++. By way of example, here is a Python program which uses many of the same functions we saw in the previous examples to build a USD curve set containing SOFR and OIS curves. The first thing the program does is to import and initialize the turbo derivatives library so that we can call it from Python. All the output from the program is displayed at the base of the page in the console window. Put some key breakpoints at certain points in the code as we step through, but you can see here that we initialize the library, and then the next key step is to actually build a yield curve set from some data that we have here a little bit higher up in the program. This builds the first yield curve set with just a SOFR curve inside it. We then display the curve set handle and display all the curves in the curve set, which in this case is just a single SOFR curve. The next thing we do is display all the discount factors behind that curve. And we then add in another curve into the curve set. So further above in the program, we've got all the data for an OIS curve. We then take that data and use it to build another curve set, this time which contains the original SOFR curve plus an OIS curve. We display the curve set handle of the built curve set. We then display all the curves in the curve set. This time the curve set contains both a SOFR and an OIS curve. And lastly, we display the discount factors of the SOFR curve once again.